Hi, everybody. Welcome to today's third webinar in our simulation series. My name is Patrick Kenny, and I'm the Senior Director of Marketing Communications for Invest Ottawa and Area X.O operated by Invest Ottawa. For those of you that are not aware, Area X.O is an Ottawa-based research and development facility featuring a 1,866-acre private testing facility, unique smart infrastructure, physical and simulated assets, and one of the most advanced communications infrastructures in the world. All this allows our clients to test and validate new exciting technologies across all sectors. This past winter, Area X.O launched a simulation discovery portal powered by ANSYS. The simulation portal and program promotes simulation and its ability to reduce time, cost, effort, and risk, and get breakthrough innovations to market faster. Which brings us to today's seminar, focused on the role of simulation in modern defense, security, and aerospace operations. Leading today for Area X.O's simulation team is simulation engineer Dr. Barry Stout, with simulation engineer Hossein Sami and business operations manager Rachel Patras supporting. Before we begin, here are a couple housekeeping items. Please enter your questions or comments in the YouTube chat. We will have specific Q&A periods, one midway through the presentation and also following the end of the presentation. Feel free to also send us follow-up questions to simulation@areaxo.com on the off chance that your questions aren't answered today. Well, let's get going. To start things off, I would now like to introduce Dr. Barry Stout, an esteemed simulation engineer with Area X.O, to provide more information on our team and to guide us through today's presentation. Barry, take it away.
Thank you, Patrick. Hello, everyone. My name is Barry Stout, and I'm here to actually talk to you about the role of simulation in modern defense, security, and aerospace operations. The agenda for the seminar is as follows. We will introduce the Area X.O simulation team. Then we will dive into what is simulation and which areas we will focus on. Then we have a brief description on finite element analysis, computational fluid dynamics, and afterwards we have a deep dive into digital machine engineering. As Patrick alluded to, we will pause for questions. So any questions we have midway through, we could answer them. So we want to make it more interactive and engaging. Thereafter the pause, we're going to continue with digital machine engineering, and then we'll do a cost model example. Thereafter, an actual example using all the simulation tools we have. Then we will have a conclusion, and then we'll talk about the simulation portal, and then we have further questions. First, I will introduce my colleague, Hossein Sami. He's an aerospace engineer with a master's degree from Carleton University. He is a simulation engineer at Area X.O with extensive experience in aerospace industries, including drones, aircraft, rockets, and satellites. About myself. So my background is in propulsion and power. So I earned my doctorate degree in propulsion, classical propulsion at York University about 10 years ago, so I'm kind of dated. And I did a postdoctoral fellowship doing work in energy systems, both in the nuclear industry and in the thermoelectrics. I started working at Area X.O since November 2022, so it's about 10 months right now. So my past work experience was mainly in defense and space, actually. And some of the work I've done is included aerothermodynamics research. I also did work in radio technology development, next generation communications, and energy systems such as thermoelectric generators and plasma torches. So what is simulation? Simulation is an artificial representation of the operation of a physical environment. They take models which represent different characteristics of the system. So let's say we have either a radio, or we have an airplane wing, or an electric motor. The simulation mimics the model with constraints in our context of physics-based. There are three types of simulations we will share in this webinar. We have finite element analysis, then we have computational fluid dynamics, and then digital mission engineering. Starting off with finite element analysis. So what is finite element analysis? Finite element analysis, or FEA, is a numerical technique to solve physics models. It takes a model and creates meshes of small elements. Each element is solved individually with initial and boundary conditions in a large matrix. One of the two FEA tools we have here at Area X.O is ANSYS Electronics Desktop. It is primarily used to simulate electromagnetism. Note that Electronic Desktop does more than just FEA. It uses other solution methods like shooting bouncing rays, but that's beyond the scope of this webinar. We have toolkits that perform FEA for antennas, electric motors, electronics cooling, signal integrity, and more. So developing robust electronics and antennas for vehicles is crucial for longevity of the missions, especially working on satellites, working with long endurance aircrafts, and so forth. So what simulation provides for electromagnetic design? So first we understand electromagnetic patterns of antennas. Then we'll also understand defining the radar cross-section objects. So let's say find like from B to a certain satellite in space or to a certain aircraft. This is also important for getting the antenna's far field pattern. Now pay attention to this feature. It will be explained later on. And finding optimal operation temperatures for the electronics. Another FEA software we have here is ANSYS Mechanical and Thermal. Both of these FEA tools are critical across industries. It's used basically everywhere. To name a few, they're used in manufacturing, aerospace, defense, and more. What simulation provide for structure design? So we look at failures of structures, so fatigue, cracks, and so forth. And then we have thermal stresses. So let's say, for example, creep from a turbo machinery blade. Also, it's also important for modal analysis. So essentially the frequency of modes and how it might provide failure during that point. Here are a couple of examples. So the first example on the top is a set of gears actually showing the total deformation under mechanical stress. And the bottom is a RC car going under thermal loading. So you see the temperature distribution in a very hot environment, like a burning building. So now we're going to computational fluid dynamics. So what is computational fluid dynamics? Similar to finite element analysis, CFD breaks down the model into little finite volumes and compute them using Navier-Stokes or heat equations. So what's the difference between FEA and CFD? Finite element analysis, FEA, converts a set of partial differential equations into ordinary differential equations and using the stiffness matrix. As for CFD, it's discretized partial differential equations and integrate them over a volume. CFD is used widely in many industries, in aerospace, naval, manufacturing, even energy systems, and so forth. So what value does CFD hold for engineers and scientists? So you can find the lift and drag of any object, like a car or aircraft, solving for structural thermal loads. So you have an aircraft wing that flying through the air at 30,000 feet. You have this CFD model. Based on that, we can get the structural thermal loading of the airframe. We can value environmental impact, so like finding the spread of pesticide from a drone spraying area. So if the pesticides spread too much and cause other damages beyond the crops. And air acoustics, so how loud the drone is operating during its operation. Now we come to the heart of the webinar, digital mission engineering. So what is digital mission engineering, or DME? It is the engineering and execution of complex missions by creating virtual representations of the environment. Systems Toolkit is a premier digital mission engineering software from ANSYS government initiatives. This product is primarily used in aeronautics, astronautics, and defense. But however, it can be used for telecommunications, agriculture, connected and automated vehicles, and more. So SDK actually creates digital twins of aerospace and ground vehicles. So you have jetliners, or like a truck, or a boat. It also does digital twins of sensors, radar, thermal, EYR, the terrain, and atmospheric conditions like rain and fog. Using digital simulations, mission engineers can explore various of what-if scenarios, test different strategies, and make informed decisions while creating costly physical prototypes. So actually, just a tidbit in the background you see, this is actually a 3D image of WorldView 3, which is currently in operation. So let's explain the typical life cycle of a DME software development. So we start by having an engineer. Thinking about a scenario, anywhere around the world. It could be the Arctic, the Middle East, Asia, Africa, wherever. Thereafter, he put his asset, whether it be a drone or a satellite or an aircraft or a ground facility, doesn't matter. These assets is performing duties such as intelligence gathering or whatnot to adversarial assets like planes, boats, vehicles, but it doesn't have to be adversarial. It could just be a piece of land. So we are monitoring infrastructure, we're monitoring an area of interest for surveillance. So our asset could be having friendlies, such like a SATCOM or a ground station. But the thing is that this is just an example, and the engineer can have any scenario they want. There are multiple iterations or multiple variations that we could do. Moving on, we are set with our scenario. Boom. Then engineer enters the simulation inputs. So this could be time of day, sensor route, maneuvers, etc. And the software runs the scenario and returns with data. The data is analyzed by engineer to see if it makes sense. So make sure it's not, it makes worldly sense. And if it does, then we can explain the outcomes. This, in a nutshell, is digital mission engineering. So let's go through some of the packages as SDK provides. So we start with coverage. It provides information on how the asset's payload, whether sensors or comms, perform in observing an area of interest. In analyzing coverage, engineers can calculate the figures of merit. So figure of merit is just a measure of performance, seeing what are we measuring, what are the key performance index we having in terms of the sensor or the communication system. So it could be the area of interest coverage in a given period of time. How long does the asset cover a particular subsection of an area of interest? So let's say you have Canada. You want to know how often does it cover Prince Edward? Where are the gaps in the coverage? So if you have the Arctic and you're having a satellite system, how often that satellite system does not spot that particular area or doesn't cover? And number of assets in a given area or subsection. So we have GPS satellites. You have at least 4 satellites available such that they could actually have a proper GPS location and more. So we go into another package called SDK Communication. So this simulates broader signal strength. It provides a range of capabilities for engineers and analysts to design, visualize, and assess various aspects of communications, such as link budget and communication coverage. It calculates link budget and returns output such that energy per bit, which is EBNO, bit error rate, carrier to noise ratio, signal noise ratio, and more. It also can implement our propagation model to observe attenuations so we can see how buildings, rain, cloud, and fog can affect signal strength. The animators show the communication coverage at the different altitudes. SDK radar simulates the effectiveness of radar systems in detecting objects. So it's basically the same electromagnetic package as SDK communication, but rather we're calling on purely radar performance. This will provide output like signal noise ratio, pulse integration, probability detection, and more. So this package also simulates the radar cross-section given from the user or been calculated and through the ANSYS products. The software has an antenna model as well for engineers to use in DMA simulation for radar as well as communication. Antenna models are implementable into vehicles, satellites, and ground stations, just to name a few. These models are including parabolic dishes, monopole antennas, phase arrays, and more. there's a heap load of antenna models. Now, remember I said about the beginning about the electronics desktop and how we could export far field patterns from the antenna. From there, we can actually input those far field patterns into SDK and that will provide a far field analysis for the radar and for communication to see how it performs using that particular antenna. So you see this video is the antenna beam pattern and how it follows the UAV during operations to keep in contact. So another type of sensor package is the Electro-Optical and Infrared, or EOIR. This pattern package simulates optical sensors at various wavelengths, from visible to thermal infrared. So we could do short wave, we could do near infrared, visible. And we can actually simulate different cameras like a standard 3 spectral band RGB, multispectral, hyperspectral, and thermal sensors. Engineers can put in the different parameters like spatial, like field of view and number of pixels, the spectral bands and resolution, the optics, such as the F number, diffraction, and radiometrics like sensitivity and range. So for explanation, on the right is the sensor drone performing a search and rescue mission and capturing images of the adult mannequin lost in the middle of the field. I know it's kind of funny. One image, which is on the top, is the thermal image. So we give this mannequin a little bit of heat signature. And on the bottom is a panchromatic. So just for those who don't know, panchromatic is basically having a visible range with no color. So it's kind of like black and white per se. Okay, so moving on. So what Area X.O has specifically with SDK is Aviator. This package specializes in aircraft flight dynamics and control. The package has both fixed wing and rotor wing models, ranging from commercial aircraft, such like the 747 jetliners or Cessna, to military aircraft like a helicopter or the F-35s. Data from the aerodynamic power plant and geometry can be fed into the flight dynamics model. Engineers can attach different payloads to the aircraft to observe the aircraft behavior. Now we have a quick pause, and I want to know if there are any questions so forth.
Yeah, Barry, I'll start off by saying I think you've done a great job setting the stage and certainly getting into some detail. And I know you're getting into some practical examples after, but I'm sure at this point there might be some initial questions. Let's see. Just a reminder, everybody, if you have any questions, just throw them into the YouTube chat and we'll bring them up on screen and get Barry to provide some detail and some responses. Barry, to kick us off, I have one that I had received previously.
Yep.
Let me just grab that one. So I'm wondering, Barry, you've gone through some examples of some simulations that are maybe commonly used or maybe becoming more commonly used. In terms of your expertise within the sector, what simulations do you think should be used that aren't being used now?
Oh, yeah, that's a good question. So when it comes to specifically for defense and aerospace, okay, there is a lack of digital engineering. So we have to have there has to be some sort of simulation to show how does the asset is being used in a given environment. So if let's say you have a new optical camera, great. So how is it perform under an environment where you want to sell it to, let's say, the defense industry in the Middle East? So you want to make sure that camera could see what it should be, and if it doesn't see it, then why should you build it? Because you could build a camera and all of a sudden you launch it. Let's say a satellite, you launch into space, and the camera has a worse detail than expected. So in that case, then you just wasted probably $10 million.
Yeah, that's a great example. I mean, anytime you can save $10 million, I think you're winning. So that's a great one, Barry.
Yeah.
Another one that I had received was, how does simulation contribute to improving training and preparedness in these industries, specific to defense, security, and aerospace?
Oh, okay. Actually, this is one we have that is not shown in our webinar. Is this we have a software called Area X, and we have this where we use a code simulator to actually train, engineers, not so much engineers, but pilots and so forth, who are actually working on drones to fly in a virtual environment, which is particularly into dark zone. The drone and robotics testing and training zone we have here at Area X.O. So rather bring the drone here or testing expensive drones, they could use our simulation platform to be able to get trained.
Got it. Thanks, Barry. And then I know we had an additional question that had come through. I'm just going to ask the team if they could throw it up. Oh, there it is. How might I test out the simulation software free of charge? So this is a good example of, in terms of the benefits of the simulation portal, Barry. Did you want to talk about that?
Yes. So basically, once you actually sign up to our discovery portal at areaxo.com/simulation, once you sign up, then you can actually ask for contacting us from the simulation team, and we could actually show you the simulation, and the actual software is free. So up to March 2024, we provide free of charge simulation support, whether the engineer wants to use it himself or they want us to do the work for them. So actually, we're doing projects right now that are free of charge for small and medium enterprises.
That's great, Barry. And then just in terms of learning just a little bit more about you, Barry, are you surprised that you're now working in this simulation environment? Is this part of your career path? What do you love most about it?
Well, it has always been a part of my career path, actually. So I did a lot of work. You have to look at my propulsion and power during a PhD and postdoc. I did a lot of work in computational fluid dynamics. I did a lot of work in simulation, and I did a lot of testing work. So essentially, I could see myself doing this basically till I retire, because simulation is so important that we can save a lot of money, a lot of cost, and we can expand simulation beyond just the standard engineering platforms. You go into deep down to the physics levels, but that requires a lot of programming, a lot of expertise, and a lot of hours.
Yeah, fair enough. Thanks, Barry. I know we'll have some more questions at the end, but if you could take us through some of those practical examples in the next part of the presentation, I think that would be great.
Okay, perfect. So as we continue, so why visual engineering SDK important? It can visualize its ISR missions. So SDK enables the visualization of complex ISRs. So we can build ISR missions with SDK involving basically Earth observation satellites, high and low altitude aerial vehicles, operating bases, area of interest, communications, and more. SDK can be used to analyze the effectiveness of the ISR missions, assess the quality of the collected data, and optimize mission parameters to achieve mission objectives more efficiently. Now, I will actually go through this in an example later on. So next slide is, we're building this up. So we want to do a mission planning for novel aircraft technologies. So you ask me, so what about simulation? It sounds compelling, but how does it good for us? It saves time and money. That's what it is. It saves time and money. Here are examples of we are using so companies can save cost. So we have a new novel aircraft technology. It's this new payload, and we want to do mission planning. So if we do under a traditional approach, so we do this in staff hours, so man hours, staff hours. So we have to build a physical scenario building, right? So we have to build this physical scenario. So in this case, we could be Area X.O, but that takes a week. So you have to set up where you want to put, let's say, certain object and assets. Then you have to configure the aircraft. So let's say this is a drone. You have to configure the drone to actually meet the requirements that you have for your sensor. And then, well, sensor or communication, but let's call it payload for now. Then we have to do a payload calculations. So you have to calculate how the payload, like what payload do you need to actually either purchase it or manufacture from scratch. So let's assume that this is a commercial off-the-shelf payload. Then you want to obtain the payload, and then you have to test it under laboratory conditions. So you have to work on that. So that takes about a week. But then you have to configure the payload in the aircraft. So we want to make sure that the payload actually matches to the aircraft, and there's no hiccups. And then you start collecting and processing the data. So basically doing the actual experiments. But then you have to go through adjusting, redesigning, and retesting. So let's say that the first test is not satisfactory. So you have adjusted, or you have to redesign it, and then retest the payload. That's about 100 hours per se. I mean, I'm just giving a low ballpark, a low ballpark. Then we have a final report, which is about a week, so which is standard. And so for the total staff hours, it's about 400 staff hours. Let's look at a simulation approach. So we build a scenario building inside of SDK, fairly straightforward, it takes about a week. So we implement the virtual aircraft, payload, assets, and other entities into the environment, which is about a little bit under a week. Then we do collecting and processing the data. So we run SDK and other software. And then we do adjusting and redesign. So you ask yourself, why the 40 hours for simulation and 100 hours for traditional? Well, for simulation, we could just change some parameters and then test it again. And then change these parameters again, change it again, and test it again. Opposed to the traditional approach, when you're going through a payload, you have to make changes to the parameters of your payload, but if your payload is not good enough, then you have to take it out and you have to redo it again. And you retest. And then you have the final report, which is the same as the traditional approach. So you have a total staff hours of about 180 hours. Now, let's take this at $165 an hour. So then when you have a subtotal project cost, that's not including maintenance, not including overhead, not including manufacturing. So we're just talking about just the building, right? Assuming that you have a free payload. That will cost about $66,000. But if you go to the simulation approach, it will cost you $29,700. So you save over $36,000 when going for the simulation approach. Now, of course, some people say, well, then we're going to build it anyways eventually. It's like, yes, but are you going to build 10 prototypes, or you just want to build 2? I'd rather build 2 prototypes that we know is near perfect than build 10 prototypes that then like 9 of them are not working properly. Now we're going to the crux of it all. So let's take an actual example. So we have a blade antenna performance over harsh Arctic conditions. So we have a team of engineering researchers, want to test a new blade antenna for signal integrity and durability using a remote piloted aerial system, so RPAS, the aerial drone. This copper blade antenna emits a 780 megahertz RF signal. The tools we can use for the multi-physics simulation is high-frequency structure solver or electronics desktop, SDK, Fluent, and mechanical. So in the mission scenario, coming from basically a CONOP or concept of operations, on October 17th, the Radiosat Constellation mission detected an unknown vessel in the Arctic. A team of security officials established a Fort operating base. The officials sent a remotely piloted aerial system to search for the unknown vessel. The drone uses its optical camera to capture images and send data to the Fort operating base from its onboard communication system. The drone expected to experience frigid temperatures from the Arctic wind. The fluctuating temperatures may affect the performance of the data transfer. So we have taken a couple of assumptions. One assumption is that the antenna does not have a resodome. Why? Is to simplify the development of the simulation, and number 2, we want to exaggerate the temperature effects of the temperature effects inside that blade. And electronics heating from the antenna system is negligible. Now, the reason why it's negligible in this case is because we want to simplify the aspects of heating when it comes to from the antenna from emitting a signal. So we don't want to model that. That will add more complexity. So again, this is a simple example. First, we'll design and simulate the blade antenna under ideal conditions. Here we have the blade antenna already created. So we have the showing the antenna and the ground bounding conditions. And then we will zoom in and we see the excitation plane, which is a simple wire. We have the main setup set across 780. So this blade antenna is designed for 780 megahertz. And then we pop it up. We have the setup to sweep across within 780 megahertz, so between 400 megahertz to 1.2 gigahertz. And we validate the simulation, and then we run it. So again, this is a simple example, and we are solving based on these conditions. This will take less than a minute. Just be patient. Well, I should be patient, actually. So now the simulation is done. So it takes a few minutes to actually just simulate this whole thing. And then we will just go ahead and check if it's done. Yes, it is done. All right. So now the first thing we're going to see is the beamform. So we see the beamforming, the antenna, the EM pattern coming from the blade antenna. And then we'll also see the gain plots for the far fields. So now, based on what we have here with the antenna pattern, we're going to go ahead and export it. So we export the far fields, and we'll say that this is for the SDK model, the SDK simulation. And that's it. Now with the standard development, we show this earth field to see the extent of this SDK environment. So we can do anywhere around the world. So it doesn't matter where you want to do it. Now we're going to close into the site alert and none of it. So we just close in, and we're just loading up the antenna pattern, showing this information, and we'll pause right here. So you see this blue blob. This blue blob is the antenna pattern that we have from the EDT. So we actually get the far field pattern and just insert directly into SDK. Continuing on. And then we have SDK Aviator. So this is where we actually design the aircraft dynamics, the flight dynamics, and the pattern. So we could actually give the aircraft a flight plan. So we can actually change the flight plan. We can actually adjust what we need on the fly, and SDK actually calculates the flight dynamics of it. And if it's an error, they will say, well, this is impossible. The aircraft might fall out of the sky, or so forth. Okay, and now we'll zoom out to the problem space. So we see our waypoints, and then we will zoom into the unknown vessel. So let's say this is an icebreaker. It's in the middle of October, and we see the flight path of the aircraft. So we know what's going to go on, and we see that this scenario is ready. And here's a snippet of the result of the simulation. This is an RPAS passing near the unknown vessel and taking images. Here's something interesting that I want to point out. You see these numbers here? This is real-time simulation of the flight pattern of the aircraft. So SDK actually calculates the downrange, how much fuel it will consume, was the wind speed, true airspeed, ground speed, even the static temperature. Now, the conditions we obtain from the SDK can now be transferred to our CFD FEA model. So what we do is we take the initial temperature of negative 11.3, which is the temperature of alert at the time of this of the scenario. So we took the inlet wind speed, so the inbound wind speed at 97.74 meters per second. That was SDK calculated. We add a crosswind speed of 10 meters per second just to give more complexity to the problem. And we put the wind temperature at negative 21.2 degrees Celsius. So even 11.3 degrees Celsius is either set by NOAA or by us looking at the weather channel and just looking at the temperature at the time. We at SDK actually calculate the air temperature at that altitude. And the material for this is copper. So the wind velocity right here is the result of the fluent simulation. Now, based on that simulation, we can transfer the information to mechanical to get the temperature and pressure results. And these will fit as initial conditions for the for the structural mechanics. The mechanical results show the total deformation and the von Mises stress. So von Mises stresses are essentially equivalent stresses. So the stress results show that there's a high concentration stress and a chance of failure at the bottom of the blade. So that makes sense because the blade tenon is acting like as a cantilever beam. And for the total deformation, we see is at the top here. As electron, and then actually transfer the deformation model into ANSYS electronics desktop, and then calculate as a deformed blade. So we see here we have the gain plots. So the plot in solid is the original on intact antenna blade, and then the one dotted line is deformed. So we see that there is very little change, and there's not significant difference in terms of performance. And then we can see that here in the carrier to noise ratio in SDK. So the green is the blade antenna intact, and while the black is the black antenna deformed. Now, of course, we have to note that it should always have a weather dome, but the thing is that, again, the point is that we want to exaggerate and show the power of simulation when it comes to predicting the performance of the blade antenna. So there you have it. So in conclusion, simulation is a powerful tool that helps with cross-analysis, so perform multi-physics analysis using multiple engineering tools, SDK, fluid, mechanical, thermal. Engineers and scientists can analyze products' performances throughout different environmental conditions. Spurs innovation and creativity without going through expensive manufacturing, and also allow engineers to optimize their designs. So join our simulation community for free. Learn about the benefits of simulation, see and interact with Area X.O's assets in a virtual environment, access ANSYS curated content, access ANSYS and MathWorks computing software, sign up to be informed about the future information sessions. Sign up is free to unlock resources, and content is only available at our Area X.O simulation community. So you can actually join in our discovery portal, which is powered by ANSYS, at www.areaxo.com/simulation. Thank you. And we're going to go through our second round of questions.
Great. Thanks, Barry. I can't get over the real world data points that can be benchmarked through simulation. It's unbelievable to me. So thank you very much for walking us through that. There was so much detail and real practical examples, and I know everybody really appreciates it. Just a reminder to everybody that any questions you have, just throw them into the YouTube chat and we will get them. And we'll ask the team maybe to throw up a couple, and we'll get into those now. Is Area X.O registered in the Canadian Controlled Goods Program, and would they accept an NDA should we wish to test a product?
Actually, those are two questions. Let's start with one. So the Canadian Controlled Goods Program, I have to go speak to our product manager, right? But I'm pretty sure it does. And And the second question is with NDA, we are subject to NDA. So whatever your product is, we will abide 100% through our NDA. Now, if we want to talk about using confidential or classified material, we won't do that. That's the only thing we're not going to do is it has to be unclassified, just for our just to make sure that we have our just to avoid any messy security issues.
Great. Great question. So thanks for posting that one. How does simulation support decision-making processes in defense, security, and aerospace?
Oh, very simple. Like, what salary are you going to use? So let's take an example of a let's say there's a military commanders in Europe wanting to monitor a certain area of interest. They want to have, let's say, these criteria. So we can simulate different satellites. So let's say we simulate a SAR satellite, a synthetic aperture radar satellite. We can start optical cameras. We could simulate lidar sensors, and these different sensors will give different outputs. So let's say for a SAR sensor, it's great for a great area of coverage, but the details is very poor compared to, let's say, a high definition optical camera, which have, let's say, 30 or 35 centimeter ground sampling distance. Then we can see the details of, let's say, again, for a military commander, tanks, aircrafts, the facility, seeing the pattern of life changes, and so forth.
Nice. That's very. Maybe a couple more questions. What future advancements or trends can we expect to see in simulation for the sector?
Oh my God. Oh, that's I'll be honest, I cannot predict that. What we can predict is that there'll be more use of simulation in terms of training pilots. So the sixth generation aircrafts that Lockheed and Northrop Grumman and other major companies are testing pilots and even teaching AI how to fly using simulation.
Yeah, good example. Maybe another one. Let's see. Oh, how can simulation be effectively integrated into existing defense systems and processes? So not something new, but something beneficial to something that's already happening.
Yes. So, okay, let's take an example of the North Warning System. So we can model the North Warning System up in the Arctic, and let's say you throw in a new satellite system to make sure that we don't have any gaps. So we can actually model the North Warning System, of course, unclassified, and then we'll throw in a new sat system, which is optical or SAR, and we can actually see how it augments the North Warning System for NORAD.
But thanks, Barry. And I think we'll take one more if we have one more. Yeah. What are the potential benefits and limitations of using simulation in the defense sector? Any limitations we should know about?
Okay, so we all know the potential benefits. So for digital engineering, we can actually visualize the scenario with the ConOps. With the limitations is essentially, are we using the real data that is provided? Because if we could go, let's say we're in the defense, we're military subject matter experts. Let's say the HIMARS. So it has a range of, let's say, 300 kilometers. I don't know, right? But do we know that? Not really, right? The only ones who know that truly is the ones who know that under secret or top secret, right? And even that, if we have to take that from there, then we have to go through a heap of hurdles to actually get that simulated. Now let's go through ITAR, International Traffic Arms Regulations. Then we go through controlled goods services. Then we have to go through security clearances. So then so the question you're asking is the juice worth the squeeze of the orange?
That's great, Barry. So you've given us a lot to think about, Barry, and a lot of great information. And I think a lot of opportunities about how the simulation portal and the simulation community can really attack some of these issues and opportunities together as we move forward. So I wanted to really thank you for the presentation and for all the information that you provided today.
No problem. And if there are any more questions, please email us. And if you want to actually test out our simulation software for free, you go at simulation@areaxo.com. Just send us an email. and we'll respond to you as soon as possible.
Great, Barry. One thing I'll mention is, it's an exciting time for us at Area X.O right now. We actually have a smart mobility demonstration day that's going to come up soon on the 27th of September. Lots of opportunities to attend there, and simulation is actually going to be featured as part of some of the different technology that is featured, which is great news. We also have our CAV Canada conference, which is a smart mobility conference taking place at Area X.O on the 28th. So 27th and 28th are 2 busy days for us, so I wanted to make sure that everybody was aware of those. And then just in conclusion, I wanted to thank Dr. Stout and all the Area X.O team members for enlightening us today. We will be following up on today's webinar with the recording, as well as a survey for everyone to respond to. If you're not already a member of the simulation community, you can register for free. There's a good amount of dialogue there and opportunities to get information first and be part of that community. So I really encourage you to do that. And if you have any questions, you can certainly reach out to simulation@areaxo.com. That's simulation@areaxo.com. I want to thank everybody for your attendance here today, and really have a great day, and we'll talk to you soon.